Hey everyone, welcome to my video on volumes of similar cross-section. Some people call this volumes by slicing. The idea is that what we're going to do is build up a volume by either slicing it into shapes that are similar. So for instance, maybe all squares or all circles or all semicircles, something like that. And compute the volume by just adding up all the volumes of the individual slices. Now what we're going to start with is actually building a volume, constructing it made of these similar slices. So, or some people call them similar cross sections. So there's a couple links here you can go to get kind of the idea. I'm going to take a look at one of those real quick. So this is the first one, and the idea is, so I have two curves here with our typical rectangle just going between those two curves. In this case, we would think of that as like a vertical line. And what I want to do is, up from that XY plane, I want to make, say, a square. And all of my cross sections that go up from the XY plane, those are going to be squares. So I might say add a few of these in here. So we're going to build up just a whole bunch of these squares, and the volume of all of those squares added together will be the volume of this solid. So we call this solid a solid that's generated by cross sections who are squares, and usually we'll specify like the rectangle is perpendicular to the x-axis, and the cross sections are going to be from rectangles perpendicular to the x-axis, and those cross sections are squares. You don't have to use squares. I could use, say, equilateral triangles, and that will change the shape a little bit. So you can tell the squares are going to give you a lot more volume there. Equilateral triangles a little bit less because they're smaller. I could also do semicircles, something like that. So that's kind of the idea on these, is that I'm just changing the shape on those specific pieces. So for instance, if I wanted to maybe get a little bit better look at just a few of these, this would be my equilateral triangles. This would be my semicircles, this would be my squares, something like that. And generally with these, we'll just be looking at, like I said, adding up a whole bunch of these over this region. Let's go and try one. So I'm going to go back to our shape here. So I got y is 1/3 x plus 6. So that's going to be this line that's right here. And I'll go ahead and put that in. So y is 1/3 x plus 6, and the parabola, which is down here, y is 1/9 x squared. So this is 1/9 x squared. And what we're going to do is we're going to draw rectangles perpendicular to the x-axis, and imagine that we have squares coming out. So very similar to the figure we just saw. So if I have, say, a vertical rectangle right here, perpendicular to the x-axis, then there's going to be a square coming out of the board right there. Now sometimes these are a little bit tricky to draw, so you got to kind of imagine a little bit of perspective on these, but I'm going to go ahead and do sort of my best. So we're going to imagine this is a square coming out of the page toward you. Something similar to this. Alright, so there's my square, and you might put in a couple of these if you want. So I could put another one, say right here. Notice this is a much longer side, so you're going to get a much larger square right there. So in general, it's just like anything else. The bigger the piece at the bottom, if everything else is equal, then you're going to get kind of a large piece there on the sides, because you do have a square. They are proportional. So a lot bigger piece right down here. Alright. And you kind of have to use your imagination, so that's why we sometimes use the software to visualize these guys, just because it is a little bit tricky to draw. Alright, so in order to compute these, we're going to start putting in some information. So for the first part, I'm just going to call the base of this square b. So this would be, say, base b. This would also be a base b, something in terms of x, but we'll just use b for now. The thickness of this square, right? So this is going to have some little thickness right here along the edge. In this case, with a vertical rectangle parallel to the y-axis, we're going to think of that as our dx, right? So that would be our dx. And then our base, right? So if we think about the square, this would be b. Down here, this would also be my base b. And this edge right here, this would be my little dx. So that's kind of what I'm thinking, is this rectangle that's sort of black right here has base b. That square also has a height b coming out, and the thickness is just that dx. So how can we write base b so that it's in terms of x? Because we're going to want to add all these up here in a minute. So what I can do is basically just look at the length of that b, right? It's this y on top minus this y on bottom. So I'm just taking whatever this y value is on top, subtracting the y on the bottom. So in our case, it's that 1/3 x plus 6 minus the 1/9 x squared. So I could say b is, and I'm going to go ahead and write in this y1 minus y2 just to re-emphasize that. And sometimes you might actually want to use those definitions in your calculator in Desmos to compute these out. And that would be this 1/3 x plus 6 minus this 1/9 x squared. Now these functions are simple enough that I don't really need a lot of parentheses on this one. Some of them though, that have longer pieces, or if you have more terms you're subtracting, you are going to need a lot more parentheses on those. Alright, so let's go and use that on the next part. So what's the volume of this cross-sectional slice? So we're still just using kind of this b idea. So the volume, right, this side is b, this is b, this is my dx. Well, we just got base times height times thickness, so this volume is going to be b squared times dx for any particular square that I'm looking at. All right, well, now we're going to add all those up, right? So this is going to be an integral that we're going to compute out. So we got the integral of this, and I'm just going to leave it b squared dx. And that we will replace that b with what we just found. So you might be doing, say, the integral of that y1 minus y2, squared dx with those definitions of y, or you might even, just replace the whole thing. So that 1/3 x plus 6 minus 1/9 x squared. And then don't forget that whole thing is also going to get squared. And then put our dx. So any of those definitions kind of applies, whichever one you want to do. If we want to see some bounds, let's go back real quick. Take a look at the bounds. So it looks like we're going over here at -6, all the way over on the right at 9. So right here, I get 9. All the way over here, -6. All right, so we'll just plug those in as our bounds and then compute that out. So if you want to go ahead and see what you get, go ahead and try to compute that out, see what you get. -6 to 9 is going to be our bounds. And pause the video, see what you can come up with, and then we'll put that answer up there. All right, so putting those in Desmos, I just went with defining my y1, y2, and using that y1 minus y2 in my square to go ahead and compute that out. So I get 312.5. So we'll go ahead and put that back in the notebook. So 312.5. If what we're going to get for that final volume. Down here, part E, there's not really anything to do on this, but it's just helpful to think about as you're working some future problems. It's really helpful to keep these three views in mind. So you kind of your cross-sectional view of, say, drawing this out with the squares or triangles or whatever it is coming out of that XY plane. The top-down view of the base region, trying to define your edges, what is that base going to be from top to bottom. And then just your general cross-section, right? So the volume of a square is pretty easy. It's just base times itself, so base squared times dx. Other shapes can get a little more complicated. You got to think about it a little bit more. So that cross-sectional view will be helpful with that. All right, we'll do a couple more examples of some other shapes in the next video, but that should give you kind of the idea of what's going to happen with a lot of these, as basically just defining what are my bases for my slices, what's the volume of my slices, and then adding those up over that whole region.